Good morning, everyone. Let's start the seminar. Okay, so today we're very happy to have Pietro here. So just a short introduction. Pietro did his PhD here at LIP, graduating from Técnico in 2016. Then he went on to do postdocs at Oviedo and also UCL in Louvain. And since last year, he's a senior researcher at Oviedo with a Ramón and Cajal fellowship and also adjunct professor at IIT Madras. He's a member of the CMS collaboration and specializes in statistics and machine learning. He's been on the CMS statistics committee, and he's been co-coordinator of the CERN inter-experimental machine learning group since 2020. So he's co-funded and is in the steering board of the MODE collaboration, which is an initiative that focuses on the concept of using artificial intelligence to optimize construction of detectors, which I think is what we will be hearing about today. So please take it away.
Okay, so it's a pleasure to be again at LIP. Every now and then I drop by, but it's always good to also interact more in seminars. Can you hear me from outside? Is the microphone, I think it's open. Should be. Can you hear me from outside? Oh.
Yes, we can.
Perfect, okay. So, thank you very much for the invitation and for the very kind introduction. So, AI-assisted design of experiments at the frontiers of computation. The idea is that
So I think that the first slide we have to change with
manually?
Yeah, and now it works.
No, but before. Well, it used to work. Okay, no problem. So, you are all in experimental physics, I guess. No? Theoretician. Good. So we are almost all in experimental physics, except for a theoretician. And but we all know, maybe I don't know. Can you see? Well, maybe yeah, maybe it's better. But we all know that the scale of experiments of today is extremely large. So this is a photo of CMS, the experiment I'm a part of, and this is a human. So this is a huge assembled detector which is made by tens of thousands of individual elements. And we spent the last 50, 60 years in particle physics tweaking each of the components that then make up this kind of detectors for performance. But the way we did it is using a paradigma that is based on improving each of the single elements of our detectors. For instance, if you have an electromagnetic calorimeter, you typically want to have the best performance for energy measurements of electromagnetic showers. If you have a tracker, you want to typically have the best momentum reconstruction and trajectory reconstruction for a track, and so on and so forth. We typically didn't really look at the final result, the joint final result. So we optimize each of the elements, then we see what we obtain. We are happy if then we can do some studies that show that we will have sensitivity for discovering, for instance, the Higgs boson. But we didn't explicitly optimize the whole thing for this. So it's, I forgot this. These experiments on top of this give us very complex data. This is a photo of an event taken from CMS. So you have protons that collide, and you have a stream of particles. You can, for charged particles, you can measure the tracks. For muons, you can measure the track, and then you detect them in the muon chamber, so in the outer part of the detectors. And all hadronic and electromagnetic showers are measured in the calorimeters in the intermediate part of the detector. And a single data point is a vector with a huge amount of dimensions, composed by with a rich structure made up of different particles that you can reconstruct. And then there are quantities that you want to exploit, symmetries, conservation laws that you want to exploit to build up your event. And in order to convert these into inference in quantities of interest, in parameters of the theory, we have a framework that we use every day, which is the likelihood principle. Essentially, we build our models by choosing a certain parameters of the model. We design a model, then we design a parametric model, and then the model consists in writing down the probabilities of obtaining a certain values for data, given the value of the parameter of the model. When we take our data, we condition this model on the actually observed data, and we obtain a function that is only a function of the parameter of the model. We maximize this function and we say we measure the mass of the Higgs boson, or we can put it into a hypothesis testing framework and say, well, the standard model without Higgs boson hypothesis is disfavored. I actually see an excess. Then you measure it and you actually observe the Higgs boson. To do this, we need to summarize all that super complex event that we have seen into simpler quantities. So the typical pipeline of an analysis in particle physics experiments goes like this. The physics generates data, generates a multidimensional, huge amount of dimensions, we have seen the complexity of this kind of events, stochastic variable. So it's a random process, and you have this variable. And then you detect it with your detector. So your detector will give some sensor readouts that will give you some quantities z as a function of the actual physics that was there and of the parameters of your detector, how we have built your detector. Then typically we want to build some high-level features, so we have all the readouts of tens of thousands of channels, but what we want to actually use is 2 muons with a PT get larger than 20 GeV, 3 jets with some characteristics. So we want to summarize, reduce the dimensionality of these data events into something that we can understand better using this kind of high-level features. And then ultimately we want to build a summary statistic for inference, so a function of the data that gives us as an output a value for the parameter of the model that we want to use to, for instance, to say the mass is 125 or we have discovered the Higgs boson. And if you have this chain, and in this chain the sensor readouts depend on the construction parameters of the detector, then also your summary statistic will depend on these parameters. And we will exploit this in the coming slides. We like low-dimensional summaries since a lot of time. So these plots are for X to gamma gamma at CMS. These are 13 TV data, so these are not the plots that were used to discover the Higgs boson in 2012, but the logical analysis is the same. So we condense all the information about the photons into a multivariate discriminator that condenses all the information into one variable to suppress backgrounds and to enhance the signal. And then we have some physical observable related in this case to the mass of the 2 photons. And then we want to do hypothesis testing here. So from super complex event to working in the end with a single histogram in one variable. Our brain does exactly this. Our brain takes some multidimensional sensorial inputs, processes them, and gives us a very simplified model representation of this data. From this rich and probably good pizza, so you see the smell, you see the thing, you have the smell, you see the whole room, but you filter it out, you think only of the pizza. We formalize a word, a concept in our mind, pizza. So we classify these things very, very quickly and very, very efficiently. If we have too many things to classify, then we discover that it's handy to start using noting things down. If we want to do complex operations, we write them down with pen and paper. And ultimately, we invented computers And we decided that they can assist us very well in this kind of endeavor. So, if this computer should assist or replace our brain, then it's natural to check if this computer, how does our brain work? Maybe building a computer like a brain is a good idea. So in the earliest 20th century, Santiago Ramón y Cajal was credited as the father of culturism. Actually, in Spain, they say he invented the culturism. So this is actual photo of him. He was very into physical activity, but he was also a very, very good investigator, and he had a microscope. He bought a microscope, and he started to look at brains. And he's the first one who started to draw what he was seeing, and he developed a prototypical theory for the existence of neurons and the fact that the brain works as a connection of elements called neurons, which have a structure that you can actually observe with a microscope. After a few years, it was clarified, but now we know that the neurons are structured like this. They take electrical or chemical signals as inputs in the dendrites. There is a cell body with a nucleus, and the electrical potential in the membrane of the cell is propagated through the axon, which is a conduct that can be even a meter long. There are neurons that connect the brain to vastly far portions of the body, and propagates this electrical signal to these terminals that then in turn will connect to the dendrites of the next neuron. So the immediate things that you can think doing is, well, okay, let's try to model this and build a computer that works like this. Well, the problem is that if you model this, you have to solve differential equations, and computationally this is quite taxing. In particular, it was quite taxing even up to not many decades ago. So in the 50s, in the 60s, with the first computers or supercomputers by the standard of them, they quickly realized that you cannot really model a realistic neuron. So they realized, yes, exactly. So they realized that you have to simplify this. And simplify this works like that. You highly conceptualize the situation as there is a function that takes inputs and gives an output. I forget completely about potentials and propagation through space, and I just say that I do a linear combination of inputs, and then I pass it, and then I pass a function of this as the output. As simple as that. It's very fast. It's very fast, and it's very easy to connect it, to connect each of these neurons with the neuron to other neurons, and to build a network that takes some inputs and passes them through all these simplified neurons called perceptrons until you get an output out of it. And then, we have devised ways of learning from this. There are three main ways. I won't enter into detail, but mostly either you can tell your artificial brain what is the result it should strive for, and then tweak your brain until it gives the good results. Or you can tell it to figure it out, or you can tell it, look, I give you a cookie if you do it better. And this actually works very, very well. But today we will focus on this first one, because for detectors is rather handy. So this first one works like this. We want to find the best values for all the parameters that characterize our network, our brain. So the weights of these, the weights that go here are parameters that we can tweak. So the idea is that the network itself is a function with some parameters. We know what is the target function, so the actual answer that we want to get. And then we can compare the prediction of our network with the actual function that we want to get. And then we can tweak the parameters, changing effectively this function, until we find a solution that minimizes this loss function, so this function that tells how bad we are doing things. And therefore we can build these landscapes, parametric landscapes of loss function, and then we want to go through them until we find the minimum of this loss function. Once we have found, and how do we do that? Well, we have to check when you change the parameters of the network, you get a different value of the loss function. So it will, you know that you will, so you calculate the loss function, you know that you do a mistake, you have an error, and then you calculate the gradient of this. So you look at in which direction should I change the parameters of the function for the error to get smaller. And so we calculate the derivative of this error. And then we propagate it with the chain rule of calculus to all the parameters to see how much do I have to change this parameter of the function of the network in order to go in the direction of minimizing this final error. And then we do that in iterations until we converge to something that hopefully represents well the world. And this was known since the 50s, or 60s, well, or 70s, well, something like this. The problem is that we have to do a lot of derivatives. And derivatives are tricky. So if you have a function, you can write code for the function. If you have a function, you can do manual differentiation, so you just take pen and paper and differentiate it. And then you can write the code for the derivative. This gives you exact derivatives, but for chains of derivatives and iterations like this is extremely unpractical because you have to code by hand huge derivatives. You can use a software like Mathematica that takes the code and does the differentiation, but you have the problem that these type of codes are not very good at simplifying the resulting expressions. So you will end up with derivatives that have huge expressions that are heavy to compute. You can do numerical differentiation, but you know that when you use the definition of derivative in a computer, you have typically ratios of small numbers, and this explodes. This is very bad. You have a running errors, and precision error. Or you can do something that was not known, which is do automatic differentiation. Automatic differentiation is a method to get exact, it's like the holy grail of this. Gives you exact derivatives without any computational overhead. Once people figures that out, then that was the explosion of deep learning. Because finally you could actually have networks that are fast to train. So how do you do that? The key intuition was that take any function that you can code in a computer, you can decompose it into atomic operations like variable assignments, or products, or sinus, or square, or cubic functions. And the key is that we know analytically the derivative of each of these simple steps. And then you can devise two methods of differentiating this function. One of the methods is based on making the derivatives of the inputs and propagating them to the output. And it's very fast if you have low-dimensional inputs and high-dimensional outputs. And the other is based on taking the derivatives with respect to the outputs and going backwards. And it's very good if you have small dimensional outputs and large dimensional inputs. Sounds like this, right? Low dimensional output, 1 or n-th dimension, and very high dimensional inputs. So we already have the hunch that reverse mode will work very well with the backpropagation. And how do we do that? Well, the forward mode is simpler. You have the equation, you write down the trace, so the atomic operations, and for each step you just store the numbers that correspond to each operation. At the same time, you take the, for instance, for derivative with respect to x0, you calculate the value of the derivative, and you track the numeric value of this. You obtain at the end the output and its derivative. It's exact derivative. The reverse mode is a bit more tricky. You have first to go through the trace up to the output, and then you start differentiating with respect to the output. So you go in cascade upwards. But the key point is that with only these going backwards, you get the derivatives at the same time with respect to all the inputs. And this is exactly the derivative that we have here. We design software able to do this. Nowadays, if you use Torch or TensorFlow or whatever, we have software that is as simple as that. You code the function, you tell it, do reverse mode differentiation, bam, you get the gradient. It's extremely efficient. Now that we have this, we could finally machine learning everything or almost everything that we see around us. And machine learning, in a way, is a way of finding mathematical representations, which is something that we do since millennia. Since millennia, we summarize a complex world into sheets of paper with drawings that schematize how the world is structured and what we have to do things, for instance, to go here from here to here. The same thing is done in machine learning. We have chaotic data sets, and our machine learning algorithm will simplify it into mathematical representations that are more easy for a given task that we want to solve. And this gives impressive results. With this automatic differentiation powered and also all the other schemes of machine learning, like particularly for cars, is mostly reinforcement learning, but still, we can drive cars nowadays. We can identify in real time cancer polyps in a rectum, and we have basically we are using machine learning for most of the activities that we are doing nowadays. Even your phones nowadays are full of AI-assisted things that do stuff. And then there was another key understanding, which is, yes, okay, we are doing deep learning, and then it's the usual thing. Back at the time there was machine learning, then to speed things up and to make it fancier, suddenly was deep learning. It's cooler because you have more layers. Conceptually it was exactly the same thing, but it's cooler. And now the new buzzword, which is exactly deep learning, but now rebranded with a new name, is differentiable programming. Here I'm a bit exaggerating. So, yes, differentiable programming is just a renaming of deep learning. But the key intuition is that differential programming means something more than deep learning. It means you design a software that is parameterized. Instead of designing your trigger software to do things, you design a parameterized trigger software that does things. And once you can parameterize something, then you can optimize it using automatic differentiation. Of course, all of this is as good as your parameterization. If your parameterization doesn't make any sense, your optimization won't make any sense. But still, if the parameterization is good, you can do nice things. So, people started to use this concept in particle physics. In 2018, there was a technique called Inferno, which consists in, so you have the typical machine learning training, but now in the loss function, you also have the systematic uncertainties encoded inside the loss function in form of the covariance matrix. And like this, the training of the machine learning classifier, for instance, is aware of the presence of systematic uncertainties, and when you get your optimal classifier, it will give you a better result, so a smaller uncertainty, when you do, for instance, profile likelihood calculations. Following step, in around 2022, I think, yes, was to do measurement-aware analysis optimization. So the key point is that you have a target. So the loss function encodes your task. So whatever you put in the loss function gives you a new target. Here, the target is to have the smallest pools on users parameters. at the end of the analysis. And then you optimize the analysis, so this optimizes the cuts of the analysis, for instance, in order to achieve the best result. So it's an automatic analysis optimization. And well, now almost 4 years ago, we started to think about doing measurement-aware detector optimization. So we have the pipeline that we have seen before, and we know that if this quantity depends parametrically on the construction parameter of our detector, then we can write a loss function that has our physics output, so how well this thing is doing inference, as a target, and then we can find the best parameters for the detector that give us the best result for inference. But I mean, this is not very useful, right? I mean, typically, you can just take the best technology that you have, the highest granularity you can possibly build, and you get the best detector. Yes, okay, who pays for it? So the key here is to add also a constraint. The cost of this setup, of each of the setups that you try, can be included in the loss function. So now instead of having an unconstrained optimization, you have constrained optimization, and you have to find a trade-off between the physics performance and the cost of your setup, experimental setup. And this is something that humans can do only in very complex, for very complex experiments, can do only to a certain extent. We are pretty good at it, but sometimes we may miss things. So the idea is to add into the loss function a cost, which represents money, but may represent also other technical constraints like geometry, position of detector modules. If you are in an experimental cavern, you cannot pass through the wall, put the detector through the walls. I mean, you must be in that box, or you build a larger box, a larger room, and things like that. You can encode all of this into, or almost all of this in the code in the loss function. So in general, the optimization will look like that. So you want to find the parameters of the construction of the detector that minimize this function, that is constituted by the physics, the stochastic process, the sensor readouts that depend on the parameters of the detector, and your cost function that weighs the desirable goals, so how well you are doing inference, with the cost of the setup. Here I should have put z of theta, with the setup that gives you that specific inference. And then you minimize the function. This is, I mean, if you have a very symmetrical situation, typically you can already know what is the best configuration just by first principles. But there are cases, and this is a paper from a few decades ago, where they try to use genetic algorithms to optimize the design of an antenna. And in highly asymmetrical cases, you can get solutions that a human couldn't have possibly designed. Turns out that this is far better than the usual, the usual antenna design. People, I mean, you wouldn't design it like this. But then, and this brings us also to the point that we also want, however, that this algorithm give us a hint of why this situation is optimal, because otherwise we would be trusting blindly these kind of things. But one thing is sure, that there are large gains to be had. So a colleague was in the board, in the scientific external board of the Muone collaboration, and then realized that if you take the original design of this muon beam experiment, and for a quantity that you want to measure q square, you can see what is the resolution on this quantity. If you try to optimize the design, even in simple ways like you just do a grid search of all the possible parameters, you can drive down by even a factor 2, which is huge in particle physics, the resolution on the physical quantity that is actually the target of the experiment. So if you can do that before building an experiment, it's fantastic, because you can use the money that you have in the most optimal way. Of course, we are not naive. We cannot parameterize everything. So typically, it's unrealistic to give the optimal solution, the one point that is the minimum of the loss landscape. So we aim at giving a hint at where is the minimum and what is a relatively well-behaved region around it that gives near to optimal solutions. And then the physicist, which is able to then encode all the things that you couldn't parameterize, like where you put a plug or things like this, will choose what is, among these near to optimal solutions, the best one. So we aim not at replacing the judgment of the physicist, but at assisting it. So we tell the physicist, look, don't waste time trying these kind of setups, but look at this region of the possible setups, and then you find what is the best one. But the cooler region to look at is this one. Don't waste time. Then, of course, you can debate on how far or how close you can be to optimality. And it also depends because, of course, I mean, if your loss landscape is very regular, even if you go relatively far from the minimum, you still aren't too close, too far. But if you have a landscape that is extremely irregular for some reason, if you do a step here, suddenly you may be in a region which is vastly non-optimal. So you have to check how is your loss landscape. Okay. I told you that you can explore these landscapes using gradient descent. But why gradient descent? Because there are several methods. The simplest one is to do a grid or random search. You just try different settings until you get the best one. Or you can use a Bayesian optimization or techniques like annealing or genetic algorithm, which consist in breeding a generation of detectors that mate with each other and then give songs that are supposedly better or not for many years. And then there are all the gradient-based optimization methods. Turns out that these methods are better or worse depending on some key characteristics. For instance, the time that is needed to process each individual sample and the number of parameters that you want to try to optimize. So broadly, you can build some conceptual diagram where you can see that grid and random search is good when you process samples quickly and you don't have many parameters. Because the more parameters you have, the exponentially larger the grid must be. Then, if you have even maybe a relatively large number of parameters and a large number of samples, you can use Bayesian optimization, simulated annealing, which are methods to run through a grid, but in a clever way, so trying to go in a good direction, which is already reminding us of gradient descent, but with different methods. But the point is that the actual methods that we know work computationally better, when you have large time per sample, typically connects with very complex events, and the huge number of parameters is gradient descent. That's why in MODE we are focusing on gradient descent methods to solve these problems. Of course, we are not able yet to optimize something on the scale of the LHC, so we try to use methods that are good here, but in a region where things are still manageable with the computer solved today. So we tried first tomography, muon tomography in particular. So the idea is that you have cosmic rays that come from the explosion of supernovae, and these primary cosmic rays arrive to Earth, and they impact with the atmosphere. They are mostly, well, they are either gammas or protons, and the rest are other elements. They impact with the atmosphere, and when they impact with the atmosphere, they produce some particles that are called muons, and muons travel for a long time through matter without interacting with it. So the muons produced in the high atmosphere can arrive to Earth. We actually have about, I think, 1 muon per centimeter per second or something, or minutes, that is passing through us at any time. So they can be used in principle to study things, to do tomography. So the way it works, you can either you have a volume that you want to scan, and then what is the idea? The idea is a muon would pass. If there is no volume, the muon will come here, will pass through your detector. If there is a volume, the muon, if the material is heavy enough, will scatter and will change its direction. Some of the muons will be scattered so much that they are absorbed by material, and therefore will not arrive here. So you can measure the difference in flux between here where you don't have your object and here where you have the object, and you can infer how heavy was the object by how many muons it has stopped or deviated. Or you can do scattering. So you have two detectors. You measure the trajectory of the incoming muons and the trajectory of the outgoing muons, and then you can estimate the scattering angle. And from there, you can invert the probabilistic relationship to get what is the radiation length of the material. And that's precisely what we did. So the typical setting is like this. So if you have a high radiation length material, so a very light material, you basically won't have scattering. But if the material is heavy, you will have, on average, larger scattering angles. And the relationship between the scattering angles and x0 is probabilistic, so you cannot infer the radiation length from one angle. You need a collection, a distribution of angles, and the function that connects the distribution of angles to the x0 will have a different spread, and the spread will determine what is the estimated radiation length. And so you can basically do a scan of a passive volume of a material to see what is composed from. And then we recently published, it's almost published, we sent the second iteration of questions. We presented it at NeuroETS a few months ago, a shorter version of that. And we recently put the code online for everyone to use, if you're interested. So we basically build a pipeline, a differentiable pipeline, where we generate muons. We can try, we have certain detectors with certain parameters. We can predict what is the composition of certain volume. We can compare it with the true generated material that we simulate. We can add to this the cost of this configuration. And then we can do the backward pass, so we can update the detector parameters in the direction of having better estimate of the radiation length and less cost. You put this in a loop and you can optimize a detector. For muon tomography, this is actually a bit tricky because there are several things that need to be taken into account. So the first thing is that to have something differentiable, all the elements of your pipeline must be differentiable. And anything that is discrete is not differentiable, typically, and therefore is an issue. For instance, what we do is we have these passing volumes, we voxelize them in layers, and then each layer in voxels. When we have a muon, we do a fit to the track, and then we estimate the angle, but when we have to assign the muon to a certain voxel of the passive volume, and when we collect lots of muon for a certain voxel, then we have a distribution and we can do inference for the x0. The problem is that, for instance, the number of detectors is a discrete parameter. So we have tricks to do that. So typically we have an efficiency that a global efficiency of the layer that can go to 0. When it goes to 0, we say there is no detector layer. For each of the panels, so each of these detector panels, these detector muons, will have a certain efficiency, but the efficiency will drop to 0 outside because so the panel is here. If the muon passes outside the panel, efficiency is exactly 0. But a function that has a certain value inside the detector and is 0 outside is not differentiable. So, what do we do? This is the first trick we do. Well, when we are doing the training, so when we are optimizing the detector, we replace the physical efficiency function with a smoothed version of it, with a sigmoid, that is differentiable. It's an approximation, but it's differentiable. So it's a surrogate efficiency. Then, when we want to evaluate how good is that fixed configuration, we put back again the actual physical efficiency function for the purposes of validation. The other thing that was actually tricky is to make the muon hits differentiable, because here we have detectors that tell you, muon passed or muon didn't pass. A hit, a yes-no, is not differentiable. So we actually convert them into a Gaussian distribution, which is differentiable. So we say when there is a hit here, we associate to the hit a Gaussian distribution picked here, and with the width, which is the uncertainty that we have on this. And no, the width is actually equal to how large the panel is. Sorry. And now we have a PDF essentially for this muon hit, and that is differential. Then, once we have these analytic, differentiable hits, you can do a track fitting, and here everything is differentiable because we can do it with pen and paper. We can solve the we can do the actual fit with pen and paper. Is a likelihood maximization, and then we can calculate the angle between the two lines. But then we have to assign this scattering to a certain point in the detector. So we have to calculate where these lines intersect. And the typical geometrical method of doing this is the point of closest approach, which means that you assume that the muons traveled here, scattered in one point, and then got out of the detector. Once we have done that, and this is purely geometrical method, you find the point of closest approach, you say it happened there. You can assign that muon to a voxel, and once you have many muons, you can infer the radiation length for each voxel. And what we get is something that, so this is the true generated volume. We have aluminum and we have lead. And I mean, this thing kind of sees that there is a lead block somewhere in the upper part of the detector. It's still not perfect, so it thinks that there is lead here when there is not, but it gets the ballpark. And if you actually, instead of doing a photo, a 3D photo, you actually summarize this into a summary statistic that tells there is lead or not, the results are actually very, very good. The problem of the point of closest approach is that it assumes one scattering in one point. What typically happens instead is that there may be a certain number of scatterings that globally make up this angle. If you assume there was only one scattering, you are introducing a bias. And that's what we actually see. Well, okay, but this is an illustration of the point of closest approach. We try to fix a bit the bias by trying to take into account the fact that we are not really certain about where this Poca point is, so we associate to it a function that basically collects the information from the nearby voxels in a way that is a sort of averaging of what we measure in different voxels, and this improves a bit the situation. But ultimately, there is always a bias. So this is the full detector optimization loop. How much time do I still have?
30 minutes.
I still have 30 minutes?
Sorry.
Oh, okay.
5 minutes. Sorry.
I have 5 minutes, okay. Okay, so, no problem. This is the full optimization loop. And this is the typical, you have epochs, you train and validate until convergence. In each epoch, we generate and scan a large amount of fictional volumes. And then we see how well we are we are reconstructing their relation lengths, and then we do back propagation and we update the detector parameters. We do that in the paper. We have a benchmark which is a liquid steel that is transported in furnaces, in industrial furnaces to fill molds. The problem there is that you can have some steel, you can have air inside the container, and then impurities. And the problem is that if you have impurities, you don't know how thick they are, so you cannot look at the bowl and say there is a certain amount of steel, because this is obscure. There may be this much of steel and this much of slag. And so we need a way, so optically you cannot do it. So we need a way of estimating how much slag there is. And we do it with the tomograph. I mean, this is really cool, because what you're actually doing is optimizing these kind of things with huge amounts of metal that goes into things. But yeah, I mean, I like it because it's super cool. And once you do that, you get some pretty nice results. So the blue is the true level of the molten steel inside the thing. In red is the prediction from the point of closest approach, optimized and so on. The point is that, as I mentioned, we are assuming only one scattering. So in the end, it turns out that the more metal you have, the larger the bias. So we have a debiasing procedure, which is the green, that gets us some results that are more in line with what we should optimize. And optimization, it's actually quite nice. So if we start, this is the material I want to scan. If we start with detectors that are like outside where the material, the volume is, the optimization tells you that you have to move them to be overlapping with the material, which makes sense. And when you do the bias correction, you actually get pretty good results. If you have already a good detector, you can still do a training and improve it to get some configuration that is slightly better. So you can do it also even if you have already an optimal solution. And the most interesting thing is that in very symmetrical cases where we know what is the analytical solution, we actually record, and these are those baselines, the blue and the reddish color. Our optimized green solution recovers what is the analytically best solution. So this is encouraging and kind of works. So to stay in the theme of heavy metal, let's talk about gamma ray. So I would love to talk about the group gamma ray, but what I want to talk about is about gamma rays. So we have already seen muons that come from cosmic rays. So we are focused on scattering with this. But in cosmic rays you get protons that are subject to these huge hadronic showers that are composed by electromagnetic showers, nucleons, other stuff, or gamma rays that give only electrons and photons and showers from these. So it would be interesting to separate them with a telescope. And SWGO, and I think at LIP there are several people that are working in SWGO, like Mario and so on. You can build a telescope for gamma rays. So the idea is that the gamma ray, so protons are here and here, and photons are here and here. So both protons and photons shower, and if at Earth level you have detectors, you can detect the secondary particles, and from there you can try to infer the shower. And these are showers that span several kilometers in some configurations. So you cannot build one detector of that size, so you must build very many small detectors and then place them suitably. And then some colleagues decided to try to optimize this. So you use Cherenkov tanks. You place several Cherenkov tanks along this space of several kilometers, and these tanks can separate with different electromagnetic, muon, and hadronic shower constituents with a certain degree of accuracy. You can have for each type of tank different experimental configurations. So the first thing you can do is to try to check with automatic differentiation what is the best of these configurations given cost and so on that gives you the best separation between the various showers. And then you plug it into also the problem of where to put all these things. Because you can put them with a certain granularity, you can try to put them, well, so to concentrate the most of them in a smaller area and then to have them more refined and so on. So you can do a lot of things. So gradient descent can help you. And the pipeline looks like this. So here is basically you simulate gamma a detector with certain parameters, you simulate showers. Here the test statistic is the likelihood ratio between was it a proton, was it a photon? So you want to separate the two hypotheses. Then you simulate gammas and protons, you compute the likelihood, you compute the variance, and you minimize the variance in your loss function. And then you update the detector parameters. Will it work? Surprisingly well. So this is actually the best example that so far we have in mode about how stable are the solutions that we can get with this kind of procedure. So each line is one training, and as you can see, the initial configuration of the detectors is vastly different. So here, the initial configuration is all the tanks that are black dots are here in the center. Here they are scattered randomly. Here they are in two rings. And then you click, you let the software do the optimization, and surprisingly, in all three cases, the solution is virtually the same. So this minimum optimal solution is actually extremely stable, and it corresponds to really a very clear minimum, a very clear optimal solution. And by the way, I don't really think that a human would have built this kind of three-shaped solution, starting from knowing that the showers are like this, right? So these algorithms are finding something that not only is stable, but is also somehow unexpected. So they seem to be useful, and we hope to make them useful in the future. If I have 1 more minute. Now, these experiments are simple, relatively simple, okay? It may take a bit to run, but intrinsically simple. There are not many parameters. So the problem is that now what we want to do is to scale to more complex problems, but we don't have yet the computational capability of arriving at the scale of LHC. So the idea is that we want to change completely the computational paradigm, and instead of having the typical perceptron-based networks that are essentially consist in matrix multiplication, we want to replace them with another paradigm which is time-dependent. So now you are trying to, instead of using perceptrons, which are very simple, you try to simulate the dynamics of an actual neuron, not with the equation that I've shown you, the Hodgkin-Sarsley, which is much more complex and difficult, but with a simplified version of it. So it's not as simple as the perceptron, but it's not as complex as the actual neuron dynamics. And it turns out that you can use that to generate binary spikes, and you can encode any function with a small number of binary spikes. And the cool thing is that depending on how big is the function and the resolution you want, you may need only a very small number of these spikes to represent completely a function. So what is the key point here? The key point is that instead of at each step of the way you have to do the multiplication of a matrix, so you have to access all the elements of the matrix and do operations on all the elements of the matrix. Here you have event-driven computation. So you only have to compute something when you have a spike, a signal that tells you now you have to compute something. And this is the key that makes a certain kind of, that makes this computation extremely time and energy efficient. And it turns out that there are chips called neuromorphic chips that implement this kind of mechanism, and now we are trying to use them to solve this kind of optimization problems. So this is very promising, and it will work well to expand the capabilities of this optimization. Down the line, we typically will want to go into the quantum computation concepts. So you know that you can encode information instead of in classical bits, in qubits. So instead of having 2 binary values, you have a full sphere, not a line, you have a full sphere of values, and you can build quantum mechanical circuits that are based on, that have all the properties of quantum systems. And the handy thing is that they are extremely naturally good at representing neural networks. Turns out that the typical unitary operations that you have seen when you study quantum mechanics, or trace of operators and so on, have immediate parallel with layers of neural networks, either information preserving or information loss, or lossless or lossy layers. And the very, very cool thing that really tells me that these can be useful for detector optimization is that these, so anything that you can write down as a quantum circuit is intrinsically, by definition, by construction, differentiable. So then you can differentiate it without any problem and in a very fast way. So this is the type of things we are trying to do now. So we are trying to optimize detectors, and to do that we have to surpass the conventional computers step. So the intermediate technology, almost ready step is to use these neuromorphic processors, where instead of discrete states we use analog signals and time-dependent signals inspired by biological neurons. And down the line we will probably want to try to use quantum algorithms. We have built a collaboration out of it. If you are interested, join us. We are very happy to collaborate and to work together. Actually, several colleagues, so we are now, we are all entering into different efforts, and muon tomography, neutron tomography, SWGO, and LEGEND, and others, and we are very interested. We are not only particle physicists, we are nuclear physicists, astrophysicists, and some very, very strong computer scientists and mathematicians. If you are still unsure, just come to Valencia. The food will be amazing. The weather will be also amazing. That's why we chose it. And as you can see, okay, apart Louvain and Princeton, we are trying to get the good places. But in any case, in September, the registrations are open. Abstract submission is open. We accept both, well, depending on how many we get, but we will accept both solutions like gradient descent based solutions for optimization of detectors, but also talks about, we have this new use case, we think it may be solvable with this, let's talk. So this is also an acceptable contribution that we would be very interested in getting from you. So think about it, we will be there. Thank you.